Hi, this is Chris again. In my last video, I had started writing Verilog code to build a circuit to multiply two 16-bit floating point numbers. At the end of the video, I had just finished a module which examines its input and determines if the value represented is an infinity, a zero, not a number, also known as a nan, a subnormal number, or a normal number. If you haven't seen that video, I would encourage you to watch it first. It's linked below in the comments, and a link should be showing in the upper right corner of your screen now. In this video, I'm going to start by describing how the module can be tested. If we're going to test the code, what should we be testing for exactly? To start, all the inputs to the module HP class are 16 bits wide. This means that the number of different input values is 2 to the 16th power, or 65,536. One place to start would be to figure out in advance how many of these values fall into each category. For example, of the 65,536 different values which can be stored in a 16-bit IEEE floating point value, how many are subnormal numbers? I'll start with an easy case. How many different infinities can be encoded in a 16-bit number? Many of you will be able to quickly guess the answer, but I want to go through the process step by step to lay a foundation for counting the other types of values. You'll remember from the previous video that each floating point number encoded according to the IEEE 754 standard has three fields: a sign bit, an exponent field, and a significand field. Look at the code for the HP class module for a moment. In particular, look at how the infinity flag is calculated. Notice that nothing in the logic equation specifies the sign bit. Since the sign bit is just that, a single bit, it's free to be either 0 or 1. That is, the sign bit can have two different values. A number can only be an infinity if the exponent field is all ones. That means that the number of possible exponents for infinities is 1. Likewise, there is only one possible significand value for an infinity. The significand must be 0. If we multiply the number of possible values for the sign bit times the number of possible values for the exponent times the number of possible values for the significand, that is 2 times 1 times 1, and the product is 2. That is, two different infinite values can be encoded, positive infinity and negative infinity. Let's move to something a little harder. How many different quiet nan values should we expect? Again, we start by looking at the logic equation for the QNAN flag from the HP class module. Like the infinities case, this logic equation is independent of the sign bit, which means that there are two allowable values for the sign bit. Also, like the infinities case, if a number is a nan, there is only one possible value for the exponent. The exponent must have all of its bits set to 1. The significand field is different. Effectively, we're breaking the significand field into two parts. The first part is bit 9. This lone bit must be set to 1. This also means that bit 9 can only have one possible value. The rest of the significand field is bit 0 through 8. This is a total of 9 bits, and the logic equation doesn't place any limits on what value can be stored in them. Since there are 9 bits, the possible number of values which can be stored in the remainder of the significand is 2 to the 9th power, or 512. Finally, we can calculate the possible number of quiet nan values by multiplying the number of possible values for each of the subfields. This is 2 times 1 times 1 times 2 to the 9th power, which is 2 to the 10th power, or 1024. How many signaling nan values should we expect to see? Study the logic equation for signaling nans. The number of possible sign bit values is 2, just like for infinities and for quiet nans, and for the same reasons. Likewise, the number of possible exponent values is 1. And like the quiet nan case, we have broken the significand field into two parts, bit 9 and bit 0 through 8. And bit 9 may only have one possible value. In this case, bit 9 must be 0. To repeat the analysis of the first three fields for signaling nans is exactly like quiet nans. You might be tempted to jump straight to the conclusion that there are 1024 signaling NANDs. Here's where things are different. Remember that for a value to be a NAND, at least one of the bits in the significand must be set to 1. For quiet NANDs, bit 9 is always set to 1, so there is no restriction on the values which can be stored in bits 0 through 8 of the significand. For signaling NANDs, at least one of the bits 0 through 8 must be set to 1. That means that we can't allow bits 0 through 8 to all be 0. Instead of being able to hold 2 to the 9th power different values, bits 0 through 8 can only hold 2 to the 9th power minus 1 different values. The number of possible signaling NANDs is 2 to the 10th power minus 2, or 1022. Let's think about this for a moment. Where did the other two values go? Those missing values are the positive and negative infinity values. Moving on, how many different zeros are there? Looking at the logic equation for the zero flag, you can probably guess this straight away. There are two possible values for the sign bit. There is only one valid value for the exponent field, and one valid value for the significand field. Again, like the infinities case, we have the product of 2 times 1 times 1, so there are two different zero values, positive 0 and negative 0. Examine the logic equation for subnormals. Again, we have two allowable values for the sign bit and one allowable value for the exponent field. Counting the number of possible values which can be stored in the significand of a subnormal number runs into the same gotcha as we had for signaling NANDs. There is one value which is not allowed. Subnormals aren't allowed to have a significand which has all of its bits set to 0. Since there are 10 bits in the significand, the allowable number of values for the significand of a subnormal number is 2 to the 10th power minus 1, which is 1023. So the number of possible subnormal values is 2 times 1 times 1023, which is 2046. Finally, consider the logic equation for normal numbers. Like every other case, we have two different values for the sign bit. Notice that for normal numbers, we have no restrictions on what may be placed in the significand. Since there are 10 bits in the significand, there are 2 to the 10th power, or 1024 different values for the significand. How many different values can we have for the exponent field? The exponent field is 5 bits wide. This means that the exponent field can hold up to 2 to the 5th power, or 32 unique values. When the exponent field is all zeros, or all ones, we don't have a normal number. So, of the 32 possible exponent values, only 30 of them are available for use as exponents for normal numbers. To get the total count of normal numbers, which can be written into a 16-bit floating point number, we multiply 2 times 30 times 1024 to get 61,440. Okay, let's check all of our work so far. We know that the number of possible 16-bit values is 65,536. If we add up the number of possible infinities, quiet NANDs, signaling NANDs, zeros, subnormal numbers, and normal numbers, do we get 65,536? In fact, we do. This is a good check on the work we've done so far in preparing to test our module. If the sum of the various types of values didn't match the total number of values which can be stored in a 16-bit field, we would know that we had made an error somewhere. Technically, one can argue I haven't proved that the counts are correct, only that one particular test didn't prove that they're wrong. Sorry for being pedantic, but it's my nature. Let's look at the test bench which I've written for the HP class module. I've been working in Vivado. This can be downloaded for free. There are other Verilog development environments, some open source, some not. That I happen to be using Vivado shouldn't be viewed as an endorsement. Here you can see the source for HP class which was described in my last video. And here is the source for the test bench I used to test the HP class module. Before looking at the code itself, notice that I named the test bench code HP class TB. This reflects one of the Verilog coding habits which I was taught. When writing a test bench, I create its name by appending _TB to the name of the module being tested, where TB stands for test bench, but you probably guessed that already. After the module header, I've declared the 16-bit vector f to hold the test input value, and 6 1-bit flags to hold the output of the HP class module. After that, you can see that I've declared a group of integers. The integer I will be used as a loop counter. The remaining integers are used to count the number of times that the HP class module detects each of the types. That is, how many signaling NANDs did we see while testing, how many quiet NANDs, infinities, etc. Next, there is an initial block. In here I initialize all the variables used by the simulation. You'll see that there is a $monitor statement which has been commented out. That was used when I was developing the code. That message would get printed every time the input value f and the output flags were updated. This was important because the final version of the test bench only prints a message when the test is done, either because all of the values have been tested or because an error was found. By using the monitor statement during development, I could see if the code was progressing as I expected. The next initial block has the actual test procedure. There is a loop which generates all 65,536 combinations, which can be stored in a 16-bit floating point number. Inside the loop is a multi-branch if statement, which verifies the results and counts each type of value which is supported by the IEEE 754 standard. The last piece of code actually wires the HP class module into the test bench. As you can see, it receives the input value f and outputs the 6 flags for each of the IEEE value types. We're ready now to look at the heart of the test code, the multi-branch if statement. The condition for the first branch of the if statement, the code tests for when the SNAN flag is set to true, that all of the other flags are set to false. It's important to test the return values from HP class this way because every possible floating point value should only fit into a single value type. If the HP class module ever determined that a particular value fit into more than one category, say a value was both a signaling NAND and a subnormal number, there would be an error. When this particular if condition is true, that is, when the SNAN flag is true and all of the other flags are false, the code increments the number of signaling NAND values which we've seen. You can see the else if clauses which follow perform a similar test for each of the other 5 value types. For example, in the next case, if the QNAND flag is set to true, the condition also tests to make sure that the other 5 flag values are false. At the end, there is an else statement which catches error cases. The code in the else clause will only be executed if there is more than one flag set for a particular value, or if no flags are set for a particular value. The else clause prints a message which helps me diagnose the failure, and then executes the $stop statement to end the simulation. If the loop completes without detecting any errors, then the code prints a message which verifies that the HP class module generated the test results I expect. I'm going to run the simulation now. In the meantime, I'm going to pause the video so you don't have to wait through the tedium. Okay, the test is completed. Let's look at the results. Earlier in this video, I took you through the process of calculating how many values of each type exist for the 16-bit format. If you'll remember, I started by calculating the number of infinities. You can see from the output that the test bench found 2 different infinity values. This matches the count which I calculated. The same goes for all the other value types. And you can also see from the test output, when the counts are all added up, that there is a total of 65,536 values tested. Again, this matches the number of possible values which can be stored in a 16-bit value. So far things look good. Before we wrap up testing, there's another piece of output which might be useful to look at, the waveform data. Here you can see that for the first test value, where f is all zeros, that the HP class module detected a 0 value. I know, that's hardly surprising. But let's dig into the waveform output a little deeper to see if the return flags transition in the way we would expect. Look at the next input value when f has the hexadecimal value 0001. As expected, the 0 flag output by the HP class module has transitioned to false. Also, the subnormal flag has been set to true. Does this match what we expect? For the input value hexadecimal 0001, we can see that all the exponent bits are 0. Since the significand is no longer 0, the only other value type possible is a subnormal, so this matches the test results. We can continue by asking ourselves how long we expect this stretch of subnormal numbers will continue. Remember that since the significand field is 10 bits wide, the largest value which will fit into the significand field will be hexadecimal 3FF. I'll jump the video ahead to that point in the waveform output and be back when I'm done. Okay, the input value for F is now hexadecimal 3FF. We can see that the subnormal flag is still set to 1. But when the value of F changes to hexadecimal 0400, we can see that the subnormal flag becomes 0, and the normal flag becomes 1. Again, we ask the question, is this what we would expect? The hexadecimal value 0400 has a single bit, bit 10, which is set to 1. This is the least significant bit of the exponent field, so the exponent field has transitioned from having the value 0 to having the value 1. If the exponent field is any value from 1 to 30, the encoded value is a normal number, so I'd say yes, that's what we expect to see here. Where will the next transition be? If you remember from when I wrote the HP class module, the normal flag is completely independent of the significand field and the sign bit. Stated another way, being a normal number is only dependent on the value of the exponent field. We shouldn't expect to see an exponent which is invalid for normal numbers until the exponent field becomes all ones. The marker for the simulation is now at the location where the input value for F is 7BFF. Breaking this value into parts, the current significand value is hexadecimal 3FF. If we shift the value 7BFF to the right by 10 bits to trim off the significand, we're left with an exponent value of hexadecimal 1e, which is decimal 30. So we're at the largest exponent value possible for a normal number. Also, because the significand is 3FF, we're at the largest significand value for a normal number. This would indicate we're at a transition point. And in fact, the waveform value shows that for the next input value of F, which is hexadecimal 7C00, that the normal flag becomes 0 and the infinity flag becomes 1. At the very next input value for F, which is hexadecimal 7C01, we see that the infinity flag returns to 0 and the signaling NAND flag, SNAND, becomes 1. Does this make sense? A value can only be an infinity if the significand field is all zeros. For the hexadecimal value 7C01, the significand has a bit set to 1, so the value must be a NAND. Also, bit 9 of the significand is 0, so this must be a signaling NAND. Can you predict where the next transition will take place? If you want, pause the video to work out the answer. If you guess that the next transition will happen at hexadecimal 7DFF, congratulations. When F becomes hexadecimal 7E00, bit 9 of the significand is set to 1, ending this run of signaling NANDs and beginning a run of quiet NANDs. There will be several more transitions after this, but you have enough information now that you should be able to predict where they'll be on your own. In the comments below, I've included a link to a GitHub repository which has the source code for the HP class module and its test bench. You can run the simulation for yourself to see if you correctly identified where the other transitions occur. Let's review what was covered in this video. This video was about testing the HP class module. Before writing a test procedure, I calculated how many values of each type there would be. That is, I computed for 16-bit floating point values how many of those values would be infinite, how many would be signaling NANDs, how many would be quiet NANDs, etc. I presented the test procedure which I wrote and explained its operation. We reviewed the output from the test procedure to verify that the results were consistent with our expectations. I left part of the review of the waveform output unexamined to allow you to test your comprehension of the material. Finally, I gave you a URL where you can download the HP class module and its test bench so you can examine the code and rerun the simulation on your own. In the next video, I'll actually begin the Verilog implementation of the multiplication operator. Questions and comments are welcome in the comment section below. If you found this video useful, please click like below. While you're at it, subscribe to the channel, then click the bell to be notified when new videos are available. Thanks.